Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of today's lecture is Contingency Tables, Associations, and Low Stakes Assessment number 5. As always, please be an attentive listener as you watch these videos. In previous sections, we looked at techniques for summarizing relationships between two quantitative variables. Remember, we got this in the form y equals mx plus b, and we looked about correlation coefficients and so on and so forth. We now look at techniques for summarizing relations between two qualitative variables. So consider the data as an example measured in thousands in this table, which represent the employment status and level of education of all U.S. residents 25 years or older. So the level of education is categorized by, these are categorical variables, did not finish high school graduate, some college, bachelor's degree, or higher. And their employment status, these are the columns of the table, these are the rows, they are either employed, unemployed, or not in the labor force. Not in the labor force means you're not looking for a job, you're not unemployed or employed, you're just not looking for a job. And this is from the Bureau of Labor Statistics. Now this is called a contingency table because the number depends. Which cell you're in depends on your status. This is also sometimes called a two-way table because it relates two categories of data. The row variable is employee status, as we talked about, and the column variable is education, and each box inside is called a cell. Okay. So what we're going to do is we're going to discuss being able to do analysis of such data. And we can ask questions and answer questions with this. For example, are individuals who have higher levels of education more likely to be employed? And so we're going to discuss both numerical and graphical methods for summarizing this data. Okay, so the first step in summarizing data in a contingency table is to determine the distribution of each variable separately. And to do this, we create what is called a marginal distribution. So the definition is a marginal distribution of a variable is a frequency or relative frequency distribution of either the row or the column variable in the contingency table. In other words, the distributions are called marginal distributions because they appear in the right and bottom margin of the contingency table. So basically what we're doing is we're adding up the rows here. We add up this row, and this row and get those numbers. We add up this column, this column, this column, and this column to get those. So if I give you a contingency table without these things added up, you certainly want to do that. A marginal distribution removes the effect of either the row variable or the column variable in the table. So to create this, calculate the row and column totals for each category. This is easy to do in Excel. And the row totals represent the distribution of the row variables, and the column totals represent the distributions of the column variable. Okay, we can also determine the relative frequency distribution. Now here was the data that we had before, but if we want to talk about the relative frequency distribution, we will take what is the grand total here. And again, remember that these are in thousands, but if we're talking about relative, the thousands will cancel out. And what we can do is we can divide the total here divided by the grand total, and we can get decimals, or you could change these to percentages. And so you see here, we see that almost 10% of the people surveyed did not finish high school. A little better than 28% were high school graduates. Around 26% had some college, and 36% or so had bachelor's degrees. Similarly, we could talk about employed, unemployed, and not in the workforce. And again, we're dividing these totals by the grand totals, and this is called a relative frequency marginal distribution. And so this is an example of that. And we can use this to answer questions, and here's a handful of questions. So what proportion of the following groups are employed? So we can say those who did not finish high school. Well, what we can do is we can look at these numbers here, and we can see that 21,980,000 individuals did not finish high school because that is this total. But then we also can say that of those 9,607 are employed. So that's the portion of the individuals who did not finish high school who are employed. So you see, we answered this question. We can say what proportion are employed? Those who were high school graduates. So we go here, we would take the 62 as the denominator, but it would be 34, and we find that that's 55.6%. For C, those who finished some college, we would take 36,370 divided by 57,400, and we would get this. And last but not least, those who have at least a bachelor's degree is here, and so we would take 57,000 and change divided by 79,000 and change, and we'll get this number here. So you see, since we were finding the conditional distribution of the employment status by level of education, the level of education is the explanatory variable, and the employment status is the response variable. We're really just answering questions such as this. Now we can also construct what is called a conditional distribution. And a conditional distribution lists not only the relative frequencies in the margin, but it lists the relative frequencies of each category of the response variable, given a specific value of the explanatory variable in the contingency table. So you see, using this data from the marginal distribution table, where we sum those, we can come up with the contingencies. So the employed is going to be, and here was the number we get, so this is 9,607 divided by 21,839. So we get 44% there. We get between 2 and 3% there, and we get 53% there. It adds up to 1 because that has to be all of the people who did not finish high school. And similarly, we can get these. So these are called a conditional distribution, and that lists the frequencies of the categories as we said. And so this is the conditional distribution. We can also use the results that we have and draw a bar graph that helps us to look at these pictures. And I could ask you, given the data, to draw a bar graph like this. I could also give you a bar graph and say, what does this say? Now this tells me that the unemployment rate across all of these educational levels, given that data, is about the same. But you can also see that the more education you have, the greater chance that you have that you are employed. And the and also the lower the chance you are not in the labor force, the more education. So this tells you a lot, and you should be able to make graphs that look like this. And as we say, it's clear as the level of education increases, the proportion of employed also increases, and as the level of education increases, the proportion not in the labor force decreases. Linda is going to show us, and I will show you too in the VCM, how to make these graphs, and that's part of the learning that we have, and that will come in the VCMs. You could draw these differently, just making different stacks, and you can show the various percentages. And you see the slivers for the brown that are unemployed is about the same for all of them, but you can make the same kind of conclusions here. And maybe this is a better chart, or maybe it's not. I don't really know, but this is another way you can make the same chart. And again, we'll show you how to do a chart like this in the VCM. The last topic we're going to do in this section is talking about Simpson's Paradox, because you see previously we talked about there could be lurking variables. We talked about that in previous videos that can make things appear to be correlated even though they are unrelated. And the same phenomena exists whenever we're looking at qualitative variables. And this is a very famous study. There was a suit brought that the University of California at Berkeley was having gender bias, meaning that they were not treating women fairly. And what we did is we looked at the admission status and gender status of students who applied to the college. Okay, so down here are some numbers that you have. And here are men, here are women, and these are the totals. This is the people that were accepted, not accepted, and so on and so forth. Well, when you start looking at this, you can see that the proportion of accepted applicants was 1748 over 4425, which is 39 and change percent. But the men were 1191 divided by 2560, and so that was 46%. And the women were, if you look at the numbers, it would be 557 divided by 1835, and that is just a little better than 30. So people looked at this and says, hey, you're taking 46% of the men and just over 30% of the women, and there's more women, so you're discriminating against us. And so a gender suit actually was brought against the university, and they were shocked and claimed that the programs of study was a lurking variable that created the apparent association between these two. And here's the defense, and I'm going to share that with you next. And this actually was a subject of an article in Science back in 1975. Okay, so here was the table that we saw, but now what they do is they break it down by various programs. And this is what was called Program A, Program B, Program C, Program D, Program E, and Program F. And what you see is that not many women applied, not nearly as many women applied to Program A as men did. And you see the same thing was true about Program B. Program C, there were a few more women. These were about balanced. This was kind of 2-to-1 women. And here there were more women as well. But some of these big programs had a lot more men who applied. And so you see, you can look this by program A, B, C, D, E, and F. And when you look at that, when those numbers, what you can see, and you can calculate for the programs what happened with the men and what happened with the women. And you can see that for program A, even though there were 314, well, let's see, that was the rejected. So, oh, this is accepted and non-accepted. Excuse me, that's accepted and non-accepted here. So what you can see is that for program A, they took 61% of the men, but they did take 82% of the women. There just were a lot fewer women. And if you look across and compare these numbers, you say here the women won, here the women won, here they were about equal, here the women won, here they were about equal, and here the women won. And if you look at the graph of this, you can see men and women, and you can see that for the most part, either they were pretty much equal, as in these four, or the women actually had a higher percentage who applied. So they use this argument and they say this is an example of a lurking variable. And so Simpson's paradox describes a situation in which an association between two variables inverts or goes away when a third variable is introduced to the analysis. So this is an important thing. It's called a paradox because this can be quite confusing. So sometimes you do have to drill down in the data. This is our example of Simpson's paradox. Low stakes assessment 5 has us doing some things here. This is about, we ask the question, does it make a difference if something is made in America or not, by age group. So these are different age groups, and it says, are you more likely, less likely, or neither more likely or less likely to buy? And we ask a bunch of questions, and this is low stakes assessment 5 that will be in your syllabus tab for you to deal with, and in the announcements we'll talk about due dates and such. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.